Hello everyone, today we are going to discuss the Fourier transform and its application on Gaussian blur. How actually the Gaussian blur is applied on an image using Fourier transform. So we will be diving deep into the mechanism how actually we convert the image into frequency domain using Fourier transform, and how do you apply actually the Gaussian blur. So you have heard about the Gaussian blur in photography, in cinematography, which makes the photo and video very aesthetic. Suppose I have to blur my background, I will be using Gaussian blur, or I have to remove some part or focus highlight on some part. Suppose this is my face and I want to highlight on my face and partially somewhat remove the background, so I will be using the Gaussian blur on the background. So my name is Trivendra Singh BISHT. I'm from Engineering Physics IIT Roorkee. Let's get started. Let us first understand the basics of the Fourier transform. So what is Fourier transform is actually, so we have an image in xy dimension. So suppose you are seeing an image which is in x dimension, this is x dimension and this is y dimension. So there are small pixels, say rectangular pixels, which contains the information of color and the intensity. Color, as you know, there are many colors, and the intensity represents how strong is the color, how lighter and how darker is the color. So when you transform or apply Fourier transform on the image, so it transforms the image to frequency domain. So what does it actually mean when we convert an image to frequency domain? How do you understand it? Well, let us first define a term, frequency. So frequency is how fast a color changes, when you move across the image. We can understand this by image you are seeing here. So here you can see a blue line. Okay, here is a white line. Here is a white line also. So this is also an image. Okay, so here is a regular area or a smooth area. So this will be covered in low frequency zone because the color is not changing with respect to space. But as I move upward, there is a blue color and there is again a white color. So there is a sudden change in color, or we can say there is a sudden change or a fast change. So the frequency will be higher. Okay, frequency means how fast the color is changing. So these details and the edges will be covered in high frequency zone. Let us understand it deeper by taking an example. Suppose you have an we have an beautiful image of a panda. So here is a regular white surface and then there is a edge of black color and then there is a background of blue color. The background is also a regular surface. Okay. So when we do the Fourier transform of this image, we will get a shape like this. So the here you can see there is a point like shape structure and two crosses. So what does this represent? Let us now understand. Here you can see there are two zones. Suppose the head, consider the face of the panda. So this is a regular white surface where when I am moving across the image, there is no change in color. So there is a low frequency. So this part of detail, so this detail will be covered in low frequency zone at the origin. So this center we may consider as origin, and as we move away from the center, the frequency will be higher. So as we move away farther and farther, so these zones will be contain the information of edges and details. Okay, so this is the basic. Let us now move on to the next part. Suppose you have another example. Here is an image of a flower. So when we do the Fourier transform, we will get images like this. So here are two frequency zone. What does this mean? Is that there are two low frequency zone, or it means in this image we got two centers of low frequency zone. As we move farther away from the center, the frequency will be higher, and the details of these images like the edge where there is fast change in color, you can assume this is red color and then its petals are of yellow color. So there is an edge. Okay, there is a circular edge which is differentiating the two color. So there is a drastic change of color, and this detail will be considered in high frequency because the color is changing very fast with respect to space. So this detail, and then this edge, the edge between the leaf and the background wall, and this edge, so all these detail where the color is changing very fast with respect to space will be covered in high frequency zones, or the region away from these two center points. So now you can guess what will be the shape if we mask these two centers. Suppose if we mask these two centers, so what will be the inverse Fourier transformation? How, what the image will look like if we mask these two centers and do the inverse Fourier transform? So earlier we had image of panda. This is the Fourier transform, and we have masked the Fourier transform with this, and now we are trying to inverse Fourier transform, so we will get the image like this. Why it has happened? Now we can see that only edges are seen of the panda. The regular surfaces, the white surfaces and the background blue surfaces have disappeared. Why? Because the regular surfaces image are concentrated in low frequency zones, and the edges and details are concentrated in high frequency zones. Okay, so you can guess what would have happened if I have marked the outer zone instead of this low frequency zone. So now this is the image of panda, and now we have masked the outer region of the Fourier transform of the panda image. Now we will try to inverse Fourier transform of this image, and we will get the same image. Why this is so? Why we are getting the same image exact back when we are restricting our frequency to only low frequency zones, and why we are not getting uh, why the edges are not disappearing? Because the edges are not sharp here. What does it mean? You can understand it by taking another example where the main object and the background are of approximately same color. Here the background, the difference between the background color and the image color is very strong. It means you can easily identify. Suppose take an example of another image like this, where object is an target with arrow and background is also approximately the same color. Here you can distinguish the background and the object, but when you try to get inverse Fourier transform of a masked Fourier transform, you will not get the same edge as before. Let us see that. So here is our image. We have Fourier transformed it, and the Fourier transform looks like this, where again we got two centers of low frequency zone. Moving farther away from the frequency zone will contain high frequency zone, where there is detail or change in color. So what guess can you make will be the shape of inverse Fourier transform of this image when we have marked the high frequency zone? As we know, the high frequency zone consists of details, edges. So the inverse Fourier transform of this image, this marked image, should have a loss of edges. So now let's take the inverse Fourier transform of this. We will get a distorted image. You can see clearly the edges has been distorted here, and there is a less distinguishment between background and the object. Why? Because the high frequency zone, which contains the details, the edges, where the color changes very fast or the frequency is high, has been removed from our Fourier transform. Okay, I think this is clear to you. So till now what we have learned is the basics of Fourier transform and how does an image looks like when it is performed under Fourier transform. Okay, so we will look upon the Gaussian filter in image processing. You can see two images here which have been applied Gaussian filter. So how this Gaussian filter actually works, we will see in the next coming slides. Gaussian blur is a type of image blurring that uses Gaussian functions. So you know that one-dimensional Gaussian functions looks like this. So our Gaussian blurring will depend upon the broadness of this Gaussian peak. So what we define here is a term sigma, which defines how broader is this peak. So as higher is the value of the sigma, more broader is the peak and more will be the Gaussian blurring and image will be more blurred. Okay, so in two-dimensional this peak will look like this two-dimensional peak will look like a fabric mesh look like this. So two-dimensional peak will look like this. So the function, the Gaussian function, the Gaussian smoothing operator. So what does it does? So this Gaussian distribution when applied to a Fourier distribution, Fourier transform of an image. So when we multiply both these, we get the output result as a Gaussian filtered image. Next, we will learn about the discretization of Gaussian functions. So there is a question mark inside the bracket. Why do we actually need the discretization of Gaussian function and what does it mean? So as you know, our Gaussian function looks like a plane, but when we discretize it to certain values, this will look like this. Okay, so the discrete Gaussian function will look like this. When we try to put this in a matrix form, it looks like this. Depending upon the dimension of the matrix, more higher the dimension is, the more accurately more pixels will be in the Gaussian peak. As higher the dimension will you go, the more pixels will be there in this Gaussian distribution. Okay, so this distribution or this matrix form, this discretized Gaussian distribution is known as Gaussian kernels. Okay, so when we multiply our Fourier transform image with these Gaussian kernels, the convolution of these Gaussian kernels with our Fourier transformed image results in a filtered Gaussian image. So how this happens and how do we do it? Let's look into the next slide. So before this, let us discuss some properties of Gaussian function. The discrete Gaussian function, or in its matrix form it is called Gaussian kernel. So Gaussian filter is a non-uniform low pass filter. Okay, why it is low pass filter? It is a low pass filter because it suppresses the noise and the background, it suppresses the details. Okay, so it removes the higher frequency and only allows the low frequency, so it is a low pass filter. Okay, so the kernel coefficient diminishes with increasing distance. So as you know, the Gaussian peak is highest at the center, and as you move away from the center, the coefficients or the weights will be diminishing. So how fast or how slower these coefficient will decrease when moving further away from the center peak will depend upon the sigma value. The sigma tells about how broader is the peak, how sharper is the peak. Okay, so central pixels will have a higher weighting value and these Gaussian kernel coefficients depend on the value of sigma. Okay, Gaussian filters might not preserve image brightness. This is also true because it when convolving with Gaussian filters, it takes out the convolution and takes out the, not saying average, but it maintains the brightness of its nearer peaks. Okay, so it might not preserve the image brightness. Let us move further and you can see a 5 cross 5 image. What does it mean? It means it has 5 pixels in x coordinate and 5 pixels in y coordinate. Okay, so at the center you have a white peak. So when you apply a Gaussian filter to it, the image will look like this. So let us move into the mathematical part of it and try to solve how it looks like when we convolve it with a Gaussian matrix or kernel, Gaussian kernel. The Gaussian matrix is called Gaussian kernel. So the discrete Gaussian matrix or the discrete Gaussian matrix, also known as Gaussian kernel, can be obtained by our Gaussian function, which is given by 1 upon 2 pi sigma square exponential of minus x square plus y square by 2 sigma square. Okay, so when you put the values of x and y or the coordinate values, and let us take sigma equal to 1. So when you try to put these xy values and sigma values, you will get a Gaussian matrix which has this form. So when we normalize this and try to get some approximate fractional values, so the Gaussian filter will be in approximately look like this. Okay, so you can see the higher weightage are at the center, and as you go away from the center, the value of these weights and coefficients decreases and diminishes, and how faster they will diminish will depend upon the sigma value. So our sigma equal to 1. So as the sigma will be higher, the peak will be broader. Okay, the peak will be broader means the values will be decreasing slowly, so our blur will be higher. Okay, this will be more clear after taking some example. Here in example 1 we have a 3 cos 3 images, so 3 pixels in x coordinate and 3 pixels in y coordinate. Okay, 1 pixel, 2 pixel, 3 pixel. Similarly in x coordinate, 1 pixel, 2 pixel and third pixel. So at the center we have white pixel. So this is our original image and this is our Gaussian filter, and this is the operation of convolution. So when we convolve our original image with our Gaussian filter, we get this Gaussian filtered image. So how we are getting, let us try to get into the mathematical part. So as you can see in the Gaussian filter, we have at the center more brighter part, and in sidewise we have less brighter part, and at the corners we have only dark black part. Okay, so when we are convolving it with this original image, this is looking like this. So how this is actually happening, let us see the mathematical part. So here is our input image, which consists of a 5 cross 5 pixel matrix. In the center you will see a white pixel whose value has been designated to 0 100, and the black pixel has been designated as 0, and any intermediate value between 0 and 100 will correspond to the color between black and white. As the value will tend to 100, the pixel will be more brighter. Okay, so this is our input image, and here is our Gaussian filter, which is 1 by 20, and this whole matrix is our Gaussian filter. As you can see at the center, there is a brighter part, and as we move away there is a less brighter part whose value is lesser than the center part. Okay, so when we convolve with this, so we will get this. So how this is happening, so how we are convolving these two matrices, we can see we just have to pull this Gaussian filter over this input image. So first of all we have to put this Gaussian filter over this input image. Okay, so match their centers. So match this 20 with this 100. So overlap this 100 and 20, match their center, and match and multiply the corresponding elements. So this 20 will be multiplied by 100, this 12 will be multiplied by 0, this 12 will be multiplied by this 0, this 8 will be multiplied by this 0, and this 8 will be multiplied by this 0. So it is like the superposition of this filter over this input image. So what you will get, you will be multiplying 100 into 20, which is here 100 into 20, multiplied by 0 into 12, 0 into 12, similarly 12 into 0, similarly this 12 into 0, similarly this 12 into 0. Okay, similarly 8 will be multiplied by 0, so divided by 20, because this 1 by 20 is there, so you will get 2000 by 20, which is 100. So the center pixel value will have value 100. Suppose you want to get this value, so now we want to get this value pixel, so we want to get the value of this pixel. So what we will do, we will superimpose the Gaussian filter and match the center of the Gaussian filter with this point. Why this point? Because we want to find this value, not this center value. Okay, so this 20 will be superimposed by 0, and this 12 will be superimposed by 100. Okay, so only 12 and 100 will make sense, will and other terms will multiply and we will get 0. Okay, so only 12 into 100 will remain. So divided by 20, we will get 1200 by 20. It is approximately nearly 60, which is equal to 61. So here one thing you have to note that I have written 60 nearly equal to 61. Why it is that so? You have to go to previous discussion 4 to 5 minutes before that during Gaussian discretization we have assumed the nearest fraction value of that Gaussian matrix. That Gaussian matrix that we were getting from the Gaussian distribution function, we have normalized it to the nearest fraction. Okay, so that's why we are getting here nearly equal, and that's correct. Okay, there is no ambiguity in that. Now let us take example 2. Here we have this original image. It is misprinted of 7 cross 7 dimension, and we are applying a Gaussian filter of 5 cross 5 dimension, and we are getting a filtered image like this. So for getting the central value, always note that the central value will be always the maximum. Why it is maximum, or we can say the full phrase of version of the center value. Why it is so? Because the Gaussian peak is highest or at maxima at its center value. Okay, to get the center value we will superimpose this 16 with 100, and this 10 will be superimposed with 0, and 6 will be superimposed with this 0, and this 6 will be superimposed with this 0, and we will, when we will multiply, we will get 16 into 100 divided by 16, which is 100. For getting this element, we have to superimpose this Gaussian filter to this center point. Okay, to this center point we have to match the center, which is 16 here, with this 0 to get this point. So when we do this, so we will get 0 multiplied by 16. Okay, that is 16 multiplied by 0, and we will multiply 10 with this 0. Okay, 10 with this 0, and for this 10 we will multiply with this 100, and other element will always be 0. So 10 into 100 will only make a non-zero sum, and divided by 16 will give you 1000 by 16, which is approximately 62, but our answer here is 60. Why it is so? Again, due to the discretized and normalized Gaussian distribution function into Gaussian matrix, we are approximating the decimal values to the fraction values. That's why this ambiguity, this is happening. Also, we have considered our range from 0 to 100 only. If we have considered from 0 to 1000, because we have considered black as 0 and white as 100, if we have chosen some more wide range, so this will be more, this would have been more accurate. Okay, so that's why here is the ambiguity, but that's correct for our this discussion of Gaussian. So for getting this point, suppose for getting this point, we have to superimpose this Gaussian center of this Gaussian filter with this point. So we have to match this center with this point. When we do this, so 16 which will be matched with 0, 16 will be superimposed by 0, and this 6 will be multiplied by 100. So only, and other terms will be 0. So 6 into 100 will give us non-zero term, divided by 16 will give you 600 by 16. Okay, which is nearly 37.5, and here it is written 36. Okay, so similarly 6 can be found, this element can be found by placing this center to here. By placing this center to here, we can get 6 here. Also we can get 6 by placing this Gaussian filter center to here, here, and add 1 to this point. Okay, so how I am doing this? Just look at the position where we are getting 6. So this is from the center. So here is our center. So 2 place up and 1 place left or right. So 2 place up, left, 1 place right. So 2 place up and then right. So we have got our center. So this is our center, and this center have to be matched with this center, and then multiply the corresponding terms and add all those terms to get this. So here is our image, how it looks like. These dimensions are mentioned wrong. It is actually 7 cross 7 image. So when we are applying Gaussian filter, we are getting this kind of image. So see how our Gaussian image has been generated. What actually Gaussian is doing, what actually Gaussian filter is doing, it is just smoothing the background. See how sharp earlier was the transition was. We have, suppose we had done the Fourier transfer of this image. So what would have been get a regular, our regular area. So we have two areas, one regular area and then edges where the color is changing very fast. So in regular area where their color is not changing very drastically, the frequency is low, and at the edges the color is changing fast, so the frequency is high. So it will be concentrated at only a center point. By doing this, so the our edge has been smoothened. However, or we can say the omega has many values now. So the details have been increased. The rate at which the color is changing or the omega has been lowered. So we have confined our image high frequency zone to the lower frequency zone. That's why the Gaussian filter is also called a low pass filter. Okay. Till now we were applying the Gaussian filter using discretized Gaussian function, which was the version, which was the discretized version of our original Gaussian function, which was e to the power minus x square plus y square by 2 sigma square type. So we have discretized it into the certain values, and then we were applying in it matrix form. So how do we apply the Gaussian filter directly in frequency domain without discretizing? So here are some steps involved. First, we have to find Fourier transform of the image. We have seen how to find the Fourier transform of the image. When we do it, our image changes from space and amplitude domain to frequency and amplitude domain. Okay, so we just overlap or we just drag the low frequency zone to the center so that it is for our easier purpose. Then we multiply with the Gaussian filter, and the equation of Gaussian filter we have seen what was it, and then we take the inverse Fourier transform. So this is our initially Fourier transform of the image. We can take the Fourier transform of the image. We have our Gaussian filter HUV, which is e to the power minus u square plus v square by 2 sigma square. U and v are nothing but the frequency in x direction and the change in frequency y direction, and sigma is the broadening factor. So when you convolute, the convolution in frequency domain is nothing but the multiplication. So when you convolute or multiply the functions in frequency domain, you will get the filtered version in frequency domain. Now to get back the frequency domain filtered image into the space and color domain, space or amplitude domain, you have to take the inverse Fourier transform of this, and you will get the Gaussian filtered image. So now I want to show you example where I have imported a image of 1280 cross 720 pixels, which is the resolution of my camera. Now I will apply a Gaussian filter on this image and see how the image will look like upon. First of all, I have masked the image so that I want to remove the background image to highlight this pink t-shirt guy. So I have just masked this guy and I want to apply the Gaussian filter on the background. So I have imported the Gaussian filter on this image, and when I increase the blurriness of the background or the sigma value, so see how beautifully the background is blurred and how the image focuses on the foreground. So this is used in photography and cinematography, where we want to highlight an object and want to focus rather than an other object, and it is a very aesthetic tool to make the photo and video look very good, and it is a very nice tool to make our photo and video to look very aesthetic and to highlight on a particular object. So that's all about this video. I hope you have understood how the Gaussian filter works actually, what is the Gaussian kernel, and how the image looks like, and how do we apply the Fourier transform on an image, and how actually the Gaussian filter is applied on an image, and how the filtered Gaussian image looks like. That's all about this video. Let's meet with some other topic. Till then, bye bye, take care.